All right, let's get right into it. We're going to do a complete rundown on how to prepare salts in a chemistry lab. My goal here is to make this super simple, super clear, and hopefully you'll see it's actually not that complicated.
So you ever look at those pictures in a textbook and see those perfect, shiny salt crystals, and you wonder, how in the world do they get them so perfect? Well, it's not magic, it's just really good chemistry. And by the time we're done here, you're going to know exactly how to do it too.
Okay, first things first, let's just do a super quick refresh. What exactly is a salt? Well, it's just an ionic compound. That means you've got a positive ion, which we call a cation, and a negative ion, an anion, and they stick together. That's it. Simple as that.
Now, here's the good news. There are a few different ways to make a salt, but you never have to guess which method to use. It all comes down to answering one single, really important question. Get that right, and you're golden.
And this is it. This is the big one. The most important question you have to ask yourself: can the salt you're trying to make dissolve in water? Is it soluble or is it insoluble? Seriously, your answer to this one question tells you exactly which path to take.
So here's your decision tree, laid out nice and clear. If the salt you want to make is soluble, meaning it dissolves, you've got two methods to pick from. But if your salt is insoluble, life is easy. There's only one way to do it. See? That's why solubility is your roadmap.
Okay, so let's go down that first path on our map. Let's say we want to make a salt that is soluble in water. Like we just saw, that gives us two possible methods, which means, you got it, we have one more decision to make.
So, what's the next question? Well, now you have to look at your ingredients, right? The things you're starting with, your reactants. Are they both soluble in water, or is one of them an insoluble solid?
And here's how that decision works. If both of your reactants are soluble, like mixing a soluble acid with a soluble alkali, then you have to use titration. But if one of your reactants is a solid that doesn't dissolve, then you use the other method. Let's look at each one. Let's kick things off with a classic example, making sodium chloride, which you probably know is just plain old table salt. Now, here's a handy tip. Sodium, potassium, and ammonium salts, you can remember them with the acronym SPA, are always soluble, and the things you use to make them are soluble too.
So, since you're starting with a soluble acid and a soluble alkali, there is only one correct method you can possibly use. You've got to use titration.
Titration is all about being super precise. First, you use an indicator to find the exact amount of acid you need to perfectly neutralize the alkali. But here's the really clever part. You then have to do the whole experiment over again, using those exact same amounts, but this time with no indicator. That way, your final salt is completely pure. After that, you just gently heat the solution to evaporate the water, and you're left with your beautiful crystals.
Okay, that makes sense. But what if the soluble salt you want isn't one of those SPA salts? What if you need to make something like those amazing bright blue copper-2 sulfate crystals? Well, in this case, you'd start with your acid, but you'd react it with an insoluble solid, like black copper-2 oxide powder.
And since one of our starting ingredients is insoluble, the name of the method is, helpfully, exactly what you're doing, reacting an acid with an insoluble substance. You gotta love it when chemistry keeps things simple, right?
So, how does this one work? The absolute key here is adding way more of the insoluble solid than you actually need. We call this adding it in excess. You do this to make sure every last bit of the acid gets used up. Then, because all that leftover black powder is a solid, you can just filter it out. What you're left with is a pure solution of your salt. From there, it's just a matter of crystallizing, filtering, and drying. Job done.
Right, so that covers both ways to make soluble salts. Let's rewind and go back to our main roadmap. What if the salt you want to make is insoluble? Well, get ready, because this path is even easier.
Let's think of a really common example. How would you go about making calcium carbonate? You might know it as chalk, or what makes up limestone and seashells. And you definitely know it doesn't dissolve in water, so it's insoluble.
For this, and for any other insoluble salt, the answer is one word, and one word only: precipitation. It's the only method you need. And this method is awesome because it's so direct. You just take two soluble solutions that contain the ions you need, pour them into the same beaker, and bam! Instantly, a solid appears out of thin air. That solid is your insoluble salt. We call it the precipitant. From there, all you have to do is filter it, give it a quick wash with pure water to clean off any impurities, and let it dry. It's probably the fastest way to make a salt.
Okay, you now know the three main methods for making salts.
So, to make sure all this really sticks in your brain, let's tackle a few of the common mistakes and trick questions that always seem to pop up. Let's do a little quick fire revision round.
First up, this is a classic exam trap. You want to make copper 2 sulfate. You've got some copper metal, you've got some sulfuric acid. It seems totally logical to just drop the metal into the acid and let it react, right? But it just won't work. Why not?
The answer all comes down to the reactivity series. Copper, well, it's just not a very reactive metal. It's too low down on the series to be able to react with a dilute acid like sulfuric acid. Nothing will happen. So the key takeaway is you have to use a copper compound, something like copper 2 oxide or copper 2 carbonate. Those will react just fine.
Okay, next one. Remember when we talked about titration? We made a huge deal about using the exact amounts of acid and alkali. Why is that precision so absolutely vital for that specific method? Here's why it's so crucial. The salt you're making is soluble, right? But guess what else is soluble? The acid and alkali you started with. So if you have any leftovers of either one, they're going to be dissolved in the water right alongside your salt. And you can't filter them out. They're all mixed together. So the only way to get a pure salt at the end is to make sure the acid and alkali perfectly, exactly neutralize each other. So there's nothing left over but salt and water.
And for our final challenge, this is a big one. We've seen that adding an excess reactant is the key to one method, but it would be a total disaster for another. Think about it for a second. Can you explain exactly why that is? If you can nail the answer to that question, you've truly mastered this topic.